Okay, this is going to be the homework set for Chapter 12. So the very first problem in Chapter 12 is we have a tugboat. Tugboat is pulling a barge, and we know that the thrust minus the drag equals the net thrust, which varies linearly with speed. So we have a little dude towing a thing, and we know that thrust minus drag equals net thrust. That varies linearly. And the tug and the barge are 3,600 kilonewtons. So we know tug and barge equal 3,600 kilonewton. We want to know time required to increase a T for the increase of V1 from 1 meter per second to V2 equals 2.5 meters per second, and B distance traveled. And we're actually given the function. So the force is represented by 81,000 minus 27,000 V. Okay. So how do we approach this? Well, we know that F is equal to MA, which means A is equal to F over M. So we know that we are moving in the x direction here. We know, and A is equal to the change in velocity with respect to time. So if we move that around, we can say A dt is equal to dv. And what we can do is we can take the integral of this term here, the acceleration, from 0 to t, and do to the integral of the velocity term from 1 to 2. And what that'll give us is if we take the integral 0 to t of a dt, we go v1 to v2 of dv, what we are going to get is, we're going to pull the a term out. What we can do is we can pull the a term out here, isolate for time by moving the acceleration term here. So we'll do that. So that is going to give us essentially from 0 to t of dt, and that is going to be equal to mass over force. And when we sub in our components, we know that it is going to be a mass. So that is going to give us a t term on the left that is going to equal 3,600 kilonewtons over 9.81. That's how we get the mass of the tug and the barge, because it's given us in newtons. So if we divide by the force of gravity, it'll give us its mass. And then we have our term here. And then we still have the integral from v1 to v2. And what we're going to do actually is for this term right here, since we do have a v term here and we are taking an integral with respect to V here, what we have to do is we have to pull that out and then put that back into our angle. We actually substitute a little bit too late. So if we pull out 27K, then we'll have 3 minus V here. So what that is supposed to look like, if you did that earlier, which you should have, not wait till the last minute to sub in your components, it's going to be 3600K in, 0.81, 27K, here will be V1, V2, and it's going to be dV over 3 minus V. Now we're talking. Now we actually have a velocity term to integrate. So integration of that is going to be, let's just put 367e to the 5th and 27k. This is going to be a natural log term 3 minus v, and that is going to be from v2 to v1. We can further separate out the components, but we know what our v2 term is, we know what our v1 is, we know it's going to be 2.5 and 1 here. So what that is going to do, let me erase some of this stuff here. So we have T equals 3.67 E5 over 27K. 3 minus V2, that is going to be 2.5. And 3 minus 1. Because natural logarithm rule, right? If you have a term that says natural log, blah, minus natural log, blah, it'll divide. And then it's going to give us 18.84 seconds when we solve for that. That's the time required. For the distance traveled now. For distance traveled, we know if we set we know our terms, right? Velocity is related to the change in distance or the change in time. We also know that acceleration is the change in velocity of the change in time. And we know that we can further manipulate that to be dt is equal to that guy. So sub this term into here so that we get a v dv term. So this is just a little bit of algebraic manipulation here. So we're going to have v equals dx, sub in for this dt term, so we don't have to worry about any time, respect to time. We just have to worry about velocity in respect to distance and acceleration. That goes there, and then what we'll have here is we're going to have velocity dv dx equal to a, or essentially acceleration adx is equal to v dv. And then further manipulation, we can go dx is equal to v dv over a. So essentially the change in distance is equal to velocity and divided by the acceleration, but the integral of it, however way you would want to say that mathematically. I am not a math major. Let's go. So we're going to have dx is equal to v dv over a. And what we're going to do here is we're going to take the integral from 0 to x, dx equal from distance traveled, v1 to v2, and if we do the same manipulation we did before, this is actually what we should have done at the beginning of the other one. I don't know why I waited until part B to do that, but I should have done it with respect to t. Because why the hell did I do that? Because essentially, if we pull out the a term, we're going to have a v dv term. So that leaves us like v dv here, v1 to v2. Okay, so, well, I kind of know why. Because when we do this term here, it's a little different than before. So we have x is equal to 3.3600 kilonewtons, I believe. Then we have the other one, k minus 27kv. Integral v1 to v2, v dv, and what that is going to do is going to give us x is equal to 3.67 e5, 27k. I'm going to do the integral v1 to v2, v dv 3 minus b. Okay. Cool. So, I don't remember how I did the calculus for that, if I'm honest, but we'll just go with it. Let's assume that Val knew how he did the integral a few weeks ago. And what we have here, we have negative v minus 3 natural log 3 minus v from v2 to v1. Sub in all our terms, our v2 term of 2.5, our v1 term of 1, and then what we'll have is we can have an x term of 3.67 e 527k, and this kind of all makes sense conceptually if you think about it. What is the distance? The distance is going to be a function of your velocity, how fast you're going, and your acceleration, because your acceleration is going to be affecting your final velocity. So that conceptually that makes sense. That's, you know, you're going to go from velocity of 1 meters per second to 2.5 meters per second, so that's going to affect your overall distance. But that transition from 1 to 2.5, yeah. So that gives us x times 13.6, 2.66, or total x of 36.17 meters. It's pretty good. It's pretty fast actually. Do you want to go from 1 meter per second to 2.5 meters per second in 30 meters when you weigh a lot? That's neat. 3,600 kilonewtons. Okay. There's the magical work for that. Okay. So we're going to go on to question 2. Question 2 from the homework set is saying, if there's a 5,000-pound truck, it's being used to lift a 100-pound boulder and a 200-pound pallet. We have the acceleration of the truck, 20 feet per second squared. We want the horizontal force between the tires and the ground, and the force between the boulder and the pallet. So, let's do this. So what we're first going to do is we're going to do a sum of the forces in the y direction. And what we have here is we have a pulley holding a pallet, right? So we're going to have that pulley, and that is going to be experiencing a certain tension force. Force of tension, tension force. And then we have the weight here. So as this is going up, there's tension here, there's tension here. So what we can say is, since it's moving up, we're going to have 2t minus weight is equal to the mass times acceleration. Conceptually, does that make sense? We have weight moving up, so the tension minus the weight equals MA. So, cool. That conceptually that makes sense. We have a 100-pound boulder and 200-pound pallet. So we can further simplify this to be 2 minus 1,000 divided by 32.2 plus 200 times 32.2 times G is going to equal 1,000 times 32.2 plus 200 divided by 30. Did I say times? I meant divide by. Because a pound force is not a mass. We need pound mass. So we divide by G sub C. Because we're crazy and we like to use imperial units. Nah, it's actually pretty cool. Once you understand G sub C, it's pretty dang awesome, especially for fluids. You just divide everything by G sub C and it's like, oh, my terms are good. Cool. My terms look weird. Divide by G sub C. No, they're fine now. So 6.211 plus 31.11. Okay, so we have our mass terms, and we have our gravity term, and we have our acceleration term. Now, the way we're going to figure out our acceleration term is by saying, if we look at our pulley, right? And the way it's going in this problem is like it's attachment point here, and then it goes like here, and then the truck's here. And that is a terrible, terrible drawing. And so what we're going to be saying is for every 12 inches of displacement here, there is 6 inches of displacement here. Right? Because we have 6 plus 6. Combined total of 12. So this does not travel as far as this does. Got it? Cool. So what we can then say is if the acceleration of the truck is 1 meter per second, then we know that the acceleration of the pulley, 1 meter per second, we're an imperial. Crazy guy. We know the acceleration at the pulley is equal to 0.5 meters per second. Feet per second. Again, why? Is because it is traveling just as far, or sorry, half as far. So we're doing 12 feet, 12 inches? 12 inches at 1 feet per second versus 6 inches. So how it's going to take us, we're going to go a little slower, accelerate slower to cover that distance. Because the one moving farther has to move faster. Okay, so that makes sense. So we'll sub in 0.5 for that. Let's see if we can simplify this a little. Well, I'll just do this. So A will equal 0.5 feet per second squared. Okay. So we have our term here. So now we can isolate for the tension. So 2 times the tension is going to be 1220.36. It's going to be this term minus this term. And that's in pound mass. Pound mass feet per second squared. That's weird. I'm just trying to wonder if I made a mistake. But damn, we'll go with it. I'm pretty confident. 610. I know I checked all my stuff earlier. I'll check that. Let me make sure that that's right. That's about right. Yeah. I'm mostly concerned about the pound force versus pound mass. Ooh, careful, don't knock that over. It's concerning, but okay. That seems like. Am I gonna go with that? Yeah, I'll go with it. Okay. So we got. Let's just go with it. We'll go with it. And we'll save that here. 610.1 pound force. Okay. Now for the truck, if we do it for your body diagram, this dude is gonna have weight here. It's gonna have force here. It's gonna have a tension here. And it's gonna have a normal force here. And it's got wheels too, which is a terrible drawing. So we know force minus tension is equal to MA. So that's cool, because then we can easily solve for force. We know I have 610.18. That is going to equal 5,000 divided by 32.2 times 1 feet per second squared. Okay, I think I figured it out. Because if we have 32.2, we have a massive foot. Massive foot pound force per second squared. Okay, what we have here is we're going to have 5,000 pound force, so 32.2. Yeah, let's go with that. So I'm getting sidetracked here. F is equal to 765.46 pound force. Let's go over my units again. It's really bugging me. It's bugging me that I can't remember my units. What's the force? What's the force, horizontal force between the tire and the ground on the truck? Okay. Now for the pallet and the boulder, let's B. We have a boulder and we have a pallet. And that is going to have, this one's a little bit counterintuitive, I thought. So here we're going to have, let's call it force AB. And here we have weight V. And we are going to have massive boulder times A. So what's happening here is, as this is going up, this is putting a force on the pallet. Yeah, that's obvious, right? That's what we're trying to solve. So if we set this up, we're going to have force on the pallet plus the mass of the boulder times gravity plus the mass of the boulder times acceleration is equal to 0. This will be over here because it equals MA, right? So, cool. So we can say the force at AB minus, oh no, that's a minus term. What am I doing? Force of AB minus weight, MBG, is equal to MBA. Shift it over, it's a positive term. Now we're in business. Okay. So we can go force of AB is now equal to 1,000 pounds divided by 32.2. So we have 32.2 for gravity plus 0.5 feet per second squared, because we know that's moving up at 0.5 feet per second squared. And working that through, we're going to have 1015.53 pound force. Cool. That's problem 2. We need a cruise, man. We're at 26 minutes. This is crazy. Crazy. It's too much time. Let's see. There's my work problems for that. Question 3. We have for question 3, we are going to have a 450-gram tether ball moving along a horizontal circular path at a constant speed of 4 meters per second. We want the angle theta of the cord formed with the pole BC and the tension in the cord. So, cool. So we want, for this problem, A, the angle theta, and B, the tension in cord. And what do we have? We have this guy right here like that. That's the ball. This is 1.8 meters. And just rotating around that. And there's our theta. It's B, C, and point A. Okay. So, what do we know about this? Well, from the problem description, it's moving across a circular path at 4 meters per second. Right? Tangential circular path, tangential velocity. So, we know that the tangential acceleration is 0 if it's moving constant, which it is. That's what the problem set defines. So, we can set that to 0. So let's do a sum of the forces in the x direction. And we know that, if we look at this guy, let's see, for the tension, this T, the tension is going to be equivalent to sine theta, T sine theta. T sine theta minus mass times radial acceleration is equal to 0. Does that seem reasonable? Is our forces in the x direction? It's not really the x direction because it's more of the it's polar x terms here. So that is going to be changing as mass rotates. That seems legit. Okay. So railroad tension sine theta is equal to our mass times, we know our, for a radial component, it's going to be like AR is equal to V squared over R, I believe. Radial acceleration, oh man, V squared R. I believe that's right. So we're going to go with it. 4 squared, 1.8 sine theta is our radius. 1.8 sine theta. So let's see, and we know that the ball, I don't know if we're doing, oh yeah, 450 grams. T sine theta is equal to 450 grams is 0.45 kilograms times 4 squared over 1.8. So what did we do here? We times still 1.8 sine theta. And to get rid of that, we can multiply sine theta. So then that simplifies that. And we just put a squared term here. So that's cool. That simplifies it a little. So now let's go over here. What we can do is we can do the sum of the forces in the y direction. And what we're going to have here is we're going to have t cosine theta, this tension in the y component, t cosine theta minus 0.45 kg, 9.81 meters per second, because that's our acceleration, is just the force, our acceleration due to gravity. We have t cosine theta is equal to 0.45 times 9.81. So we have tension ends up being equal to 4.4145 cos theta. So now what we can do, we are actually going to take this equation and we're going to sub it into this equation, because here we have two unknowns. Here we have two unknowns, two equations, two unknowns, fantastic. So it's going to be 4.4145 cos theta, sine theta, 0.45, 1.8, I believe. Let me see, 4 squared divided by 1.8 times 0.45. Let's make that 4. Sine over cosine is the magical tangent, I believe. Or actually, no, we can do that, and we're going to get really confused, because it's going to just give us another term, and we're just simplifying, we're making it more complicated. So we're going to keep that sine theta. For a second there, I was like, ooh, I see an out with a tangent, but now you don't see an out, you're fooled. It's a trick, don't do that. What we'll actually do is we're going to use our trigonometric identity. And if I recall correctly, when I did this originally, I totally had to look up that section, because I was like, what do I do now? But now it kind of seems a little bit more good. It seems more good. So now we have that in terms of cosines. So that's cool. So what we're going to do is we are going to shift all this crap around, because it's not nice. We are going to divide by 4.4145. Now we're going to multiply through 1 over cosine, so that's going to give us 1 over cosine minus cosine. And that's going to equal 0.906. And that's not a very happy term now, is it? So let's multiply through by cosine. We have that goes to 1 minus cosine 2 theta, 0.906 cosine theta. That's pretty cool. That's good, because then we can essentially treat it like a quadratic. So if we treat it like a quadratic, quadratic for the win. What we go like, say, x squared plus 0.906x minus 1 equals 0. We can solve that. That's great. What that is going to give us is we're going to have essentially x is equal to 0.644, or cosine theta is equal to 0.644. And then what we can do the, oh shoot, there we go, theta is equal to inverse tangent, or inverse cosine, blah, 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 49.9 degrees. Now, let's take this known, and we plug it into this unknown, and we're going to have t equals 4.4145 cosine 49.9, and that gives us 6.853 newtons. So, we found the angle, and we found the tension in the cord. Here is the magical reel, yeah. Okay. Problem 4. Problem 4 has a wrecking ball doing wrecking ball stuff, which is usually knocking down stuff. Because it's a wrecking ball. And wrecking balls like to do that. Wrecking balls like to wreck stuff. Okay. So we have a wrecking ball. One 30-pound Just kidding. I think I was thinking of the BC Boys. Check it out. So I was like, wreck it out. And that's not how it works. It doesn't make much sense. Steel cable. And we want the top of swing, see, and we want the bottom swing, where speed is equal to 13.2 feet per second. Let's draw a thing. Right? That's, can we call that B? No, we can't call that B. Let me do the actual drawing of the thing. So that is going to be like here. And then that's a little lighter. We'll go here, let's see. And then straight down from the vertical is D. And then we have this guy here, and that's C. And this is equal to 20 degrees. Okay, so let's look at C, and we'll draw a free body diagram. And the best part about a free diagram is it's free. Yeah. It's a stupid joke, but it's really funny. I have friends that are engineers, and I told them that joke. I gave credit where credit was due to who made the joke. They laughed. We all laughed. Okay. B equals 0. And we know our tangential acceleration is equal to 0. Tangential? Why tangential? Radial. It stopped at 0. Okay. So, let's do the sum of the forces in the weird angle direction. We're going to have T, the tension in the cable, minus the weight of this guy weight cosine 20. Let's think about this for a second. We have weight coming down. We want this component here. If weight is here, cosine adjacent to that, so we'd have a triangle going this way. Yep, it's cosine 20. Now we know the weight is 130, so we can go T is equal to 130 cosine 20, and then T is equal to 122.21 pound force. So that is the tension on the cable at the top of C. Neat. At the point D, we have to do D. This point is a straight vertical point. We can do an easy sum of the forces in the y direction. And what we're going to have is going to have tension. We're going to have weight. And that is all going to equal tension. We're going to have weight. That is going to equal mass times velocity, or velocity, mass times acceleration in this radial direction from the point. So we're going to have is that correct? Tension minus weight minus, yep, that is correct. So we know that the acceleration here, acceleration in the radial is equal to v squared r. We will set tension is going to be equal to 130 pounds divided by 32.2. Or no, I don't think we need 32.2 because we're going pound force. We're going pound force. This pound force and pound mass stuff, it's just like, is it a 32 weight? It should be a pound force, not a pound mass. That's fine, whatever. We'll ignore that. I'm not even tripping here. Okay, so what's going on here? We have 45 feet, we have 130, and we have the velocity at the bottom of the swing, given here. And that's not that bad. Plus 130 is the weight. So that'll give us pound force. I don't like that. Give me 1 second. I'm going to go through my math one more time. My notes were wrong. I was right. I forgot to put the G sub C in my notes. Or my homework, whatever. I saw it and I'm like, no, weight is a pound force, dude. You need a pound mass. So if you need a pound mass, divide by that. Nice try, thou. Yeah. Booyakasha. That's pound mass. And then we're doing the whole thing to it. So it turns into a pound force. Okay. Cool. And there's the word for that. Pound 5. I think we're doing pretty good time on this one. We're doing pretty good time. Pound 5. Turntable built on stage. I knew it. I was like, man, that doesn't look right. I'm kind of glad I caught it. Okay. We have a turntable built on the stage for use in a theatrical production. It's observed during the rehearsal that a trunk starts to slide on the turntable 10 seconds after the turntable begins to rotate. Now the trunk undergoes a constant tangential acceleration of 0.24 meters per second. Determine the coefficient of static friction between the trunk and the turntable. Okay, so we want this guy. Coefficient of static friction. Not to be confused with the coefficient of kinetic friction, because that's different. Okay. We can do a drawing. Let's do a drawing. I did a drawing. Why not? That's what's happening. So, we have constant tangential acceleration of 0.24 meters per second. And radial acceleration, or normal, I don't know how you want to call it. I call it. It really just depends what situation I'm in. I'll be like, yep, that's the normal component of the acceleration. Or whatever. If we look at it from the top, we're going to have this thing going on. And we're going to have a component here. And we're going to have a component there, right? And then we're going to have this component here. Normal, tangential, total. Right, so as it's rotating, as something rotates, the way I think about this, that I think helps me a lot, is if you've ever been to Lagoon and you go to the rapids and you stand at the edge of that dock that's rotating, it is like wanting to throw you out. I think of that as the normal acceleration. But if you're able to just hold on, you're experiencing a tangential acceleration. And those combine give you the total acceleration that you're experiencing. So that actually helps me a lot to solve problems. So we have component here, and component here. And we know this one's 0.24. And we know that we can solve for this one. Let me look at my notes real quick and see how I did that. Yep. So we use the kinematics equation where V is equal to V SO plus AT. And what we do is we have a zero initial velocity. And that just goes to AT. So velocity is equal to 0.24 tangential, normal, I don't quite remember. And the radius is, the time is 10 seconds. So that gives us a V of 2.4. So now, and I believe that is in the tangential direction, but the normal force is just the velocity in the tangential direction, I believe. I don't quite remember, but let's go with that. So we have a 2.4 tangential velocity, and the radius, we know that to be, is it given? I'm pretty sure it's given. Yeah, it's giving in the diagram, 2.5 meters. So that gives us a 2.304 meters per second. And now we can set it here. 2.304. And if we do our Pythagoras hold me back, that's the joke, I guess. The Pythagoras theorem will give us 2.316 total. Because we're doing a squared plus b squared equals c squared. So, that's cool. We now have our total acceleration. That's neat. So what we can do now is if we do a sum of the forces in the y direction, And we have to have that because we're not just, this trunk's not just going to slide out because of the normal or the tangential acceleration. It's going to combine because it's the total component. So it has to have both. So we did need that. It's not just for fun. We have normal force. And we have the weight. Some of the forces in the x direction is force here. Let's call it F because we're so unique. And here we're going to have friction force. Friction force is going to be coefficient of static friction times the normal force. So we can say coefficient times mass times gravity is equal to mass times A total. Right? So that gives us the coefficient of static friction as a ratio 2.316 over 9.81. And what that does, the units obviously are going to cancel out. It's going to be 0.236. Cool. So that is that problem. Our next problem, problem 6. Okay, yeah, we have problem 6. I'm getting bored of this color. Let's get a different color. Orbit of Venus is nearly circular with an orbital velocity of 126.5 times 103 kilometers per hour. Knowing that the mean distance from the center of the sun to the center of Venus is 108 times 10 to the 6 kilometers, and that the radius of the sun is 695 times 10 to the 3rd kilometers. Determine the mass of the sun, the acceleration of gravity, and the surface of the sun. The acceleration of gravity at the surface of the sun. Whew, that's asking a lot, man. A, we want the mass. Ooh, this is a nice color. I like this color. It feels like a hopeful color, which is what I'll need for this problem. Okay. So we know big R. That is Sun to Venus, right? Big R. 108 E 6 km. And we know little r. No. Let's get the velocity first. Velocity is 126.5 E 3 km per hour. And we know I don't know why I have G written in my notes as this. This is a pretty weird term. I have G written as, oh, that's a constant. 6.673 E minus 11 Newton per meter squared over kg squared. I'll have to double check why I have G. I don't quite remember what G is. I'll double check my notes. Okay. The equation we're looking for is, we have an equation that says velocity is related to G dot ms over r. It's constant times mass of the sun over r is equal to velocity. So essentially we are saying that velocity squared is equal to gms over r. And we can solve for the mass of the sun by saying that. So that's neato bandito. Let's go back over here. Now we can make big R. We know it's 108 e to the 6 kilometers. Times it by 1,000 to get meters. We're going to have 108 e9 meters. For velocity, this guy right here, we're going to times by 100 to get meters, and we're going to divide by 3,600 seconds to get 3.5 E4. And E is reflect the times 10 to the negative, or times 10 to the whatever. It's just a shorthand. So now, I think G is the gravitational constant, but I don't remember why. I'll have to double check that. So what we're going to have is we have a relation here for the mass of the sun, and that it's going to be related to, well, everything you just saw. Okay, and there we go. Man, see, you know, it's like, so G, I knew it was a gravitational constant, I just didn't remember exactly in that equation. It's been a minute. You know, it's crazy what you can remember sometimes, because I was not planning on remembering that. I was like, what is that? And I was like, oh yeah, the gravitational constant. So that's kind of nice. That your brain doesn't let you down all the time, just most of the time. Newton, meter second, kilogram squared. Okay. And let's do a unit check. Yeah, because this is, yeah. So if we do a unit check, times meters per second, squared, over Newton per meters per second per kilogram squared. What happens? That guy goes out, that guy goes out. Cool. And then we have, that is going to be meters per second squared over kilogram per meter per second squared times 1 over kilogram squared. And it's going to flip over. And that's going to, and you're going to have kg. Yep, cool. So we're going to have 1.98 E. Don't do that. E 30 kg. That's the mass of the sun. Now, if we want to get the gravity at the surface of the sun, what we can do is we go back to our equation. It's not really our equation, it's just an equation. We know the force of gravity to big G, massive sat, massive central, over R. And I don't quite remember how we came about to have that. But that is essentially going to equal mass times gravity, right? The force here. So, the mass, so that's going to eliminate that guy Oh, sorry. So force of gravity, or force, gravitational constant, difference in the masses, that should be an M. Mass of satellite, mass of the central body, so you have like big body, little body, rotating around it. And then the differences between them creates force, gravitational force, I guess. So mass under gravity, and we want to, this mass is going to represent the mass of the satellite. So essentially we're going to have gravitational constant times the mass of the central body for the radius. So that is going to mean G is equal to 6.673 E minus 11, and then all its crazy units. We'll include those because you never know. Over kg times, that should be squared, times 1.98 E 30 kg. We figured out here. And that is going to be a radius E 6 meters squared. And that is the radius of the sun. So that gives us 273.54 meters per second squared, which, holy cow, man, that's crazy fast. It's like, what would that do to your body? If you're used to 9 meters per second, you're increasing it by a lot. 9 meters to 273 meters. What's that delta? Jesus, it's like, well, it's like 27 times bigger. Yeah, that's about right. That's a lot. That is a lot of times bigger. 27 higher force? Yeah, that's a lot. Okay, this is the end of part 1.